So how did Bohr figure out the energy levels for this atom? It's a hydrogen, by the way. And it works for other systems too. So it would also work for a helium that if you take off an electron, it would work for a positive helium, or it would also work for lithium, 2+. So it works for one electron systems. So the way he proved that his model was correct, and it kind of is and it kind of isn't, but it's a great starting point, and it's the best way to draw an atom on the board without it looking confusing, is he began with the wavelengths that the hydrogen light gave out, and then he figured out that that must be the separation between the two of these, and he just basically had to do a lot of iterations and playing around with numbers until he figured out an equation that matched, that let us predict the energy of an electron here versus an electron there. So the electron, or the equation that he ended up with, was that the energy an electron would have to have in any orbital of hydrogen was related to negative Rydberg's constant, hang on a second, 1 over Ni squared. So this is going to look kind of weird at first. You're going to think, oh, this is a really messy equation. It's actually not messy. This right here is a constant. And I will say there are a few versions of the Rydberg constant, and it depends on what unit you want the unit to show up to be in. So we're going to use 2.19 times 10 to the minus 19th joules. We're using this constant, but again, like I said, you can look up and you can find other constants. They're just in different units. You kind of use the constant you want that works with the equation that you like. They are technically the same constant. It's just, again, rearranged into different units. So that's always the number that'll go in front. So we'll make this look a little bit easier. Negative 2.19 times 10 to the negative 19th joules. And then 1 over. Now this N thing, it's actually really easy. If the electron is on the first energy level, N is 1. If it's on the second energy level, N is 2. If it's on the third, it's 3. Are you following the trend here? So if I'm like, hey, what's the energy of the electron in the first energy level at its ground state? You would put 1 squared. So the energy of that electron is negative 2.19 times 10 to the minus 19th joules. Isn't that nice and easy? It's not actually a hard equation. It's beautifully simple. So I'm going to let you go ahead and think this through. How would I change this equation if it was on the second energy level? Right, I would just be changing this bottom number here. The constant doesn't change, 2.19 times 10 to the minus 19 joules. And now, instead of it being 1 over 1 squared, it's 1 over 2 squared. And if I put that in my calculator, 2.19 e to the negative 19th times parentheses 1 divided by 4, I get negative. I didn't put my negative in the equation, but there is a negative right here. So negative 5.22 times 10 to the negative 20th joules. And so I'm hoping you can see, and you can go ahead and calculate the energy for this n equals 3 electron in the problems. Now there's another point of interest with this, and it's, can you make the difference between here? So an electron with this energy versus an electron with this energy, the difference between the two of them, if that matches with the energy that is kicked out of the atom and that we see as light, that's the proof. So how do you get the difference between those two energy levels? You just subtract. So this is if the electron goes from n equals 2 to n equals 1. We already have the 2 equation. Negative 5.22 times 10 to the minus 20th. And then minus negative 2.19 times 10 to the negative 19th joules. So it gives us negative 5.22 e to the negative 20th minus negative 2.19 e to the negative 19th. And that gives us that the energy difference is 1.668 times 10 to the minus 19th. That's energy. Now, we know how to convert energy into wavelength. So energy is equal to hc over lambda. I'm going to rearrange it for lambda. hc over energy. So now I can say 6.626 times 10 to the negative 34th. Three times 10 to the 8th divided by 1.668 times 10 to the negative 19th. If that matches with one of the lines that we see in the spectrum, then it's a great proof, especially if it works every time for all of the different distances. So 6.626 e to the negative 34th times 3 times 10 to the 8th divided by, 1.668 the negative 19th. So that gives us 1.191 times 10 to the minus 6th. And this comes out to be in meters, and I actually want it to be in nanometers. So 1 times 10 to the minus 9th meters in 1 nanometer. Equals a wavelength of 1191 nanometers. So then we have to look it up and see if hydrogen gives us that.